Hello students, my name is Abdul Bari. We are discussing a particular topic in the subject of fluid mechanics along with a set of questions. The topic today I have chosen is hydrostatic forces. Previous session, 3 days back, we have discussed the preparation strategy. Today we'll start with the topic. The topic we have is hydrostatic forces. Hydrostatic forces. To understand the concept of hydrostatic forces, let us briefly revise the concept of loading acting on a beam. So imagine you are having a simply supported beam. Let us say this over here is a simply supported beam. On this simply supported beam, let us say you are having some loading acting this way. There is some intensity of loading which is gradually growing up till this value. This intensity of loading, let us say, is represented by W. W over here stands for load per unit length. W stands for load per unit length. If I ask you what is the net force acting on this particular beam, what would you answer? Most probably you're going to answer whatever is the area under this loading, whatever is the area under this loading, that is equal to the force acting. How do we get that idea? We realize over here intensity is load per length, therefore differential force over here or differential resultant over here must be equal to W multiplied to differential length. Let us say we go at some distance, we identify some W, and let us say we understand that this W is remaining constant for a very small portion dx. So now W multiplied with this differential length is going to give me the differential force acting over here, dr acting over here. So if I wish to find out the complete resultant, I can say it is equal to integral W dx. That is basically equal to area under this loading curve. Something very similar is happening in fluid mechanics also. Let us try to understand that. Imagine in place of a beam, you are having a plate. Suppose you are having some interface over here. Let us say this is some interface over here. The fluid present below this interface has property gamma, specific weight is gamma. Let us say it is exposed to atmosphere, therefore the gauge pressure on top over here is equal to 0. Let us say I am having a plate, a thin plate, extremely thin plate. That plate I have taken and I have submerged that plate inside over here. When I show that plate submerged inside this particular fluid, in the front view you are not able to see the actual shape of the plate. Let us say you are only able to see a line something like this. This line over here, let us say, is representing the front view of the plate. Let me choose this particular point as some point M. Let us say this point over here is a certain point N. If you wish to imagine the actual image of the plate, let us produce over here two imaginary perpendicular lines. Let us say we produce two imaginary perpendicular lines and let us show the plan view of this plate. Let us say the plate is something like this. This, let us say, is the plate we are having. This is end M, this is end N over here. Fine. Now come to think of it, the moment this plate is being submerged, imagine thickness is 0, mind you. The moment you submerge this particular plate, on every differential area there is going to be some pressure intensity acting. For example, you take a position, let us say, there is a particular position over here. This position, let us say, is at a depth of h. So over here there has to be a pressure intensity acting. How much is the pressure intensity over here? Pressure has to be equal to gamma times h. Is it not? Now this pressure intensity is acting over here. Same pressure intensity is acting on the lower side also. Okay, lower side also same pressure intensity, because we are assuming the thickness of this plate is 0. Therefore the pressure intensity on either side is going to be same. This upper side pressure intensity is pushing it down, lower side is pushing it up. Therefore, the net force acting on this differential area is going to be 0. Likewise, you imagine every differential area is experiencing a downward thrust as well as an upward thrust. Therefore, the net force acting on the plate is 0. But let us say, for the sake of understanding, we are only taking one side of the plate. If we choose only the one side of the plate, I'll be having some pressure over here. And as I keep on going down, by the virtue of increase in depth, the intensity of pressure keeps on increasing. Let us say the intensity of pressure is keeping on increasing. The pressure I have over here is equal to Pm, let us say. The pressure here is Pm. One moment, please. The pressure over here is Pm. This pressure is Pm. And as you are going down, the pressure has increased to Pn, let us say. And this pressure is keeping on increasing like this. Now, what is, I want you to imagine both these two. One second, please. I want you to look at these two diagrams over here. If you look at these two diagrams are looking very similar. On the left hand side, what you have is a beam whose length is defined. On the right hand side, you are having a plate whose area is defined. On the left hand side, the intensity of loading is load per unit length. On the right hand side, the intensity of loading is pressure, that is load per unit area. And the way the intensity of loading is varying, similar way the intensity of loading over here, that is pressure, is keeping on varying. The pressure also is keeping on varying. I hope you are able to create some similarity between both these things. Now let us come back over here. Okay? Now if I ask you the intensity of loading over here, P, you would say it is load per area. Previously W was load per length. This is load per unit area. Therefore, if I ask you what is the differential force acting, let us say over here. One moment, please. Let us say over here there is a differential force acting. There is a differential force acting. If I ask you what is the value of differential force, what would you answer? The value of differential force over here is equal to intensity of loading multiplied to a differential area corresponding to that position. So P times dA would give me the differential force. If I wish to find out the net force acting, then I'll have to integrate this thing. So net force over here would be equal to integral PdA. Integral PdA. And this integration is supposed to be exercised over the entire area of the plate, capital A, let us say. And this force over here is known as hydrostatic force. This is known as hydrostatic force. It is called as hydrostatic force. So how do we define this hydrostatic force? We define hydrostatic force as the net force acting by the virtue of hydrostatic pressure intensities on one side of a plate. We are only looking at one side of a plate. When the plate is submerged inside a fluid. Again, mind you, we are only looking at one side, because if we would look at both the sides, then the hydrostatic force would get nullified, because you are having a downward thrust as well as an upward thrust. Both of them would get nullified. So the net force acting on one side of a plate by the virtue of hydrostatic pressure intensities is known as your hydrostatic force on one side of a plate, mind you. Now, let us come back again to the beam. We understand beams very well, so let us come back over here. After having found out the value of resultant force, let us say, if I wish to ask you where is the resultant force located, then most probably you are going to answer the resultant force is located at the centroid of this particular area formed. So let us say the centroid of this area is coming over here. This is a centroid of area. Through this particular point, you are going to have net force on this particular beam passing. Now, if I ask you how did you find out this particular idea, how did you get this idea that the net force is passing through centroid of this area? The logic is very simple. In mechanics, you must have come across a concept known as Varignon's theorem. What does Varignon's theorem say? Varignon's theorem says that when you are having a set of forces which are creating a moment about a particular point, their resultant is also supposed to create same moment. For example, let us say this point over here, I am choosing as some point O. Then this dr is creating some moment about point O. Likewise, you are having infinite drs and all of them are creating some moment about this point O. So now you can say net moment about point O is equal to how much? It is equal to, now differential moment would be equal to how much? Dr times, let us say we have gone some distance x over here. Dr times x, this is the value of differential moment. If you integrate this from x is equal to 0 to L, you will get the complete moment. Now according to Varignon's theorem, this moment must be also equal to moment of resultant. So let us say it is equal to resultant times, let us say resultant is located at some distance d, so resultant times d over here. According to Varignon's theorem, the net moment by the virtue of all the drs must be equal to the moment of resultant also. Using this particular idea, we get that the net force is supposed to pass through centroid of this particular area. Something similar is happening over here as well. Come to think of it, over here you realize that all these differential forces, let us say, are creating some moment about this particular point O. Suppose we are having some point O over here. Okay, 1 minute please. So we are having some moment, differential moment over here would be equal to how much? Differential moment about point O would be equal to differential force multiplied to, let us say this distance over here is some distance y. This distance is y. Okay. Now net moment must be equal to integral of this thing. It is supposed to be integral of df times y. And according to Varignon's theorem, it must be equal to the moment of net force also. So imagine the net force is located somewhere over here. The net force is located somewhere over here. The net force is located at this particular point. This is F, let us say. And let us say the location of F from this point O is equal to some distance y star. Example sake, the distance is equal to y star. So Varignon's theorem says that this must be F multiplied to y star. Okay. The point at which this net force is concentrated, that point for us is known as center of pressure. So we are having two concepts till now. One concept is hydrostatic force, which is a net force acting by the virtue of hydrostatic pressure intensities. And the second concept is where is this force concentrated? The point at which this force is getting concentrated, that point is known as center of pressure. Think logically, where should center of pressure be concentrated? For example, in this particular case, if let us say the centroid of this particular plate is over here, what would be logical? Would the center of pressure, is the center of pressure supposed to be at the centroid, below the centroid, or above the centroid? How to get this idea? You can get this idea by thinking that the intensity of loading on the upper portion of G is lesser and the lower portion of G it is greater. The intensity of loading is, or intensity of pressure is greater. Since the intensity of pressure is greater on the lower side, therefore the net force should polarize towards the lower side. So your center of pressure therefore is coming below center of gravity or centroid of this particular plate. It is coming below center of this plate. Are you following this thing? Acha, had the plate been in a horizontal position, imagine, had the plate been in horizontal position, every point would have same depth from interface. If every point would have same depth from interface, then every point is supposed to have same intensity of pressure. It would become something like a UDL. Only in that situation, center of pressure would coincide with center of plate. Again, I am repeating, had the plate been horizontal, imagine that the plate is horizontal. Had the plate been horizontal, the intensity of pressure throughout would be same. In such a case, there is no polarization of intensity of pressure on either side of G. Since there is no polarization, whatever point G you are having, same point would become my center of pressure as well. But right now in an inclined, any random inclined position, I am supposed to have center of pressure below the centroid of this plate. Now let us say, whatever distance we are having between these two, this distance of offset we call as eccentricity. The distance of this offset is called as eccentricity. Eccentricity is basically your eccentric nature is the opposite of concentric nature. Now you see over here point G and point P are concentric. Now they have created some offset in this particular situation. So concentric's opposite is eccentric. Therefore this distance is over here called as eccentricity. So now we have three parameters of interest. First parameter of interest is the hydrostatic force. Second parameter of interest is the location of the center of pressure. The location of center of pressure can either be given by Y star in inclined position, or more preferably it can be given by this vertical distance that is given by H star. And lastly, the third parameter of interest for us is this eccentricity. So three things we are having. Let me take a fresh image to show these three parameters to you. 1 second please. Let us see. We are having certain interface. This, let us say, is the interface we are having. The gauge pressure on top is equal to 0. Gauge pressure over here is equal to 0. Let us say we have over here a plate. Let us say I am representing that plate by Mn. This is how I am representing the plate. If I produce the line of this particular plate, if I keep producing the line of this plate, the plate, let us say, is coinciding at this interface, point O. The angle of inclination of the plate with respect to the interface is theta. Okay? We have already seen that this is having some area. Let us again produce the area. 1 moment please. Let us say this is the area we are having, Mn, let us say, Mn over here. The actual area, capital A, let us say, is the area of this particular plate. Capital A is the area of this plate. Now there is going to be a center of this plate, which we have mentioned some time back. This is the center of this plate, G. And in this particular case, center of pressure is supposed to come below G. The only time center of pressure can coincide with G is when the plate is in horizontal position. Now, if I produce this G back on the front view, this is the front view. You can only see a line, mind you. So, if you produce this front view, if you produce G back on front view, this point comes as G. Likewise, if you produce over here, this point comes as your center of pressure. Okay. If I measure the depth from interface up till here, this distance, if I measure the depth from interface up till here, this distance is represented by H bar. This distance is represented by H bar. So how do we define H bar? H bar is the location of center of pressure from the interface in a vertical direction. From zero pressure line till the center of plate, if you come, that distance is known as your H bar. Likewise, some time back I have told you that if you, 1 moment please, if you measure this distance, the vertical position of center of pressure with the interface, this distance over here is known as H star. This is called as H star. And finally, should you measure the distance between point P and point G, this distance over here is known as eccentricity. So we have these three things, H bar, H star and eccentricity. Apart from this, you should know that the hydrostatic force acting is supposed to be perpendicular to the plate at point P. This is the hydrostatic force acting. This is an image you are having right now. Now over here, there are three formulas of interest to us. What are the three formulas? I am not doing derivation, I have shown you how the derivation is done. I will straight away give you the formulas over here and let us try some problems. What are the three formulas? The first formula over here is regarding hydrostatic force. This is the first formula. The value of hydrostatic force is given by gamma into area into H bar. This is a formula. The formula for hydrostatic force is specific weight multiplied to area multiplied to h bar. Mind you, h bar is the vertical distance from zero pressure line up till the center of the plate. The second formula we are having is the formula for H star. What is H star? H star is the vertical location of center of pressure from the interface. If you think logically, H star is greater than H bar. So I can write over here H star is equal to H bar plus some value. Okay. H bar plus some value. How much value? The value now, additional value over here is I sine square theta upon area times h bar. It is I sine square theta upon area times h bar. This I is a very important parameter. What is this I over here? 1 minute please. What is I over here? I is the area moment of inertia. Area moment of inertia of the area of the plate about an axis. Now see, this axis is supposed to have three properties. Okay, because people do a lot of mistake in this I, that is why I am mentioning this axis is supposed to have three properties. The first property is passing through G, because you can have multiple axes, infinite number of axes are possible. Passing through G, first thing. Second thing, it should be lying in the plane of the plate. The axis is supposed to lie in the plane of plate. And finally, it is supposed to be perpendicular to the front view. Now, if it is lying in the plane of the plate, you cannot see the axis in the front view. And it is perpendicular. That means this is the axis I am speaking about. About this particular axis, you are supposed to find out the area moment of inertia. So, perpendicular to front view. So imagine you are having an axis lying in the plane of the plate perpendicular to front view. That means it is perpendicular screen you are seeing. It is perpendicular screen. Now you cannot view that particular axis unless you look at the plan view. So imagine this axis, if I show in the plan view, then it is going to become this particular axis. So I is the area moment of inertia of the plate about all these things. If you keep in mind these 3 points, you will not do any mistake in finding the value of I. Lastly, we have a formula corresponding to the value of eccentricity. The formula for eccentricity is given by E is equal to, it is very simple actually, eccentricity value is. Now if you think, this is basically the vertical projection, I sine square theta by area h bar. If you think about it, it is a vertical, 1 second please, excuse me. It is the vertical projection of eccentricity, because you see, this is that portion, I sine square theta by area h bar is this portion. Now I want this portion. So whatever this portion is, if you divide it by sine theta, you will get this portion. So all I have to do is additional value, you divide by sine theta. So you are going to get I sine square theta divided by sine theta will give me sine of theta only upon area h bar. So this is the value we are having for eccentricity. So this completes the set of formulas we have in the case of hydrostatic forces acting on a flat plate. I hope all these formulas are clear. 3 formulas we have. First formula is for hydrostatic force, that is equal to gamma area h bar. Second formula is for h star, location of center of pressure, h bar plus I sine square theta upon area h bar. Now I sine square theta upon area h bar is the additional value we are having. If you look at its inclined value, that means you divide this particular portion, whatever portion you are having over here, whatever portion you are having over here, if you divide by sine theta, you will get back the value of eccentricity. So eccentricity is equal to I sine theta by area h bar. These are the formulas we are having. Let us look at a problem very simple problem based on these formulas. Okay. Look at this particular problem, very extremely very simple problem. I am moving out of the screen so that you can see the question clearly. This could be a 1-mark question in your GATE examination, or it could be a question in IES examination. The question says the height of a water in a vessel is h. The vessel wall of width b is at an angle of theta with respect to the vertical. The net force exerted by the water on the wall is equal to how much? The net force exerted by water on the wall is equal to how much? Let us see how do we solve this thing. We know that net force has to be equal to how much? Net force has to be equal to gamma times area times h bar. Now gamma is rho g. Okay. Area is equal to how much? Let us look at the value of area. The value of gamma is equal to how much? Rho g. Okay. Area over here has to be equal to how much? The value of area is, now you see, the plate is starting from here up till here. This inclined length is the length of this particular plate. Compound it with b because the width over here is b. How much should this inclined length be? We know that according to this particular diagram, if I produce this triangle, this is h. If this is h, this inclined length over here has to be equal to how much? This has to be h by cos theta, h divided by cos theta. So now I can say the value of area is L multiplied to B, that is equal to h by cos theta multiplied to B. In other words, you can say HB secant theta. HB secant theta. This is the value of area. The value of h bar. H bar is extremely simple over here. You see, h bar basically is a distance from the zero pressure line. Now this is zero pressure line exposed to atmosphere, therefore zero gauge pressure. From zero pressure line up to the center of the plate, how much vertical distance we have? Guaranteed it is going to be half the value of h. It is going to be half the value of h. Therefore, this is supposed to be h by 2. You have gamma, you have area, you have h bar. Therefore, you can now say the value of force has to be equal to how much? It has to be equal to rho g multiplied to hb secant theta multiplied to h by 2. So, h square b secant theta divided by 2. This is the value of force. Look at the options. 1/3 is wrong. Half b square b h square rho g, again wrong. Half rho b square g secant theta. Option C happens to be correct over here. Option C happens to be correct. I hope this question is clear. You can once view the solution if you want. Now, there is an alternate way of solving these problems. The alternate way is an analytical, geometrical method basically. If you recall, in the case of loading on a beam, we generally say the net force acting is area under the curve and the location of the force is centroid. Something similar is happening over here also. Over there, a length was there on which intensity of loading was there. Therefore, area was being formed. In our subject, we already have an area as a base on which intensity is acting. So, on an area, if you produce a height, that is compounding to give you a volume. So, in our subject, when you show a 3D picture of the loading, it is going to represent a volume. So, imagine this over here is the plate we are having. Let us say this is the plate we have. This over here is a plate we are having. On this plate, let us say there are some intensities of pressure. For example, this we have mentioned as Pm some time back. And let us say over here you are having some Pn. We have some Pn. Take it. Likewise, every differential area is supposed to experience an arrow in the name of pressure. Take it. let us say you create all those arrows, and once you create all those arrows, it forms a 3D picture. Let us say that 3D picture looks something like this. The 3D picture looks something like this. Likewise, you'll be having arrows. I'm not producing all of them, it would rather look shabby. So please try to imagine this thing. So you're having some 3D picture. Now, mind you, over here initially the pressure is less, and as you're going deeper, by the virtue of increase in depth, the pressure has increased. Now, if you think about the heights over here, the heights over here are pressure. If the heights over here are pressure, you can say the differential volume of this particular diagram is equal to base is differential area. Let us say base is differential area multiplied to the heights over here. Each height is representing a pressure. And we know that P times dA represents what? It represents differential force. So the differential volume we have is equal to differential force. That means the net volume of this particular diagram has to be equal to complete hydrostatic force we have. And this particular volume we are going to call as pressure prism. We call this particular volume over here as pressure prism. So what is a pressure prism? It's a 3D picture of all the intensities of hydrostatic forces acting on a particular plate. On one side again. Okay, always we are looking at only one side. The reason being, if you look at both the sides, the net value would rather become 0. There's no point of looking at both the sides then. Okay, na? The pressure prism basically is the net, the 3D picture produced by showing the intensities of forces. The advantage of drawing pressure prism is, first thing you identified over here is, volume of pressure prism has to be equal to hydrostatic force. Next thing, this volume is supposed to have a centroid. Imagine the volume itself is having a centroid. This is the centroid of pressure prism. Please don't get confused. There is a centroid of plate. That's a different thing. This is centroid of plate. That's a different story altogether. There is a volume centroid also. The volume you have generated, its centroid also is present. Let us call it as centroid of the pressure prism. This force must pass through the centroid of pressure prism. Just like previously in the case of beams, you are saying the net force acting was through the centroid of the area formed. Likewise over here you are having net force over here passing through this particular point. Net force is supposed to pass through. If the net force, that is hydrostatic force, is passing through this particular point, then wherever this arrow is going to strike the plate, that particular point would become which point? That point is supposed to become center of pressure. So this is the force you are having, and this is the center of pressure you are having. And you should be in a position to answer this. What should this distance over here become? This distance over here is the eccentricity. The offset distance between centroid of plate and center of pressure is known as your eccentricity. So the two advantages of drawing this pressure prism is, if you measure the volume of pressure prism, that should give you hydrostatic force, and hydrostatic force must pass through the centroid of pressure prism. The centroid of pressure prism. It must pass through centroid of pressure. Particularly the second point will be very helpful in cases where you are having a rectangular plate, especially when one end is exposed to atmosphere. Okay, second point will become particularly important. If you have understood this thing, let us go further to solve a question. One of the very good questions to have been asked, to have appeared in GATE examination mechanical paper, very good question. Okay, and this question was the application of the concept what we have studied. Let us look at that question. You can, one second please. You can read this question for yourself. It's a very interesting question. It appeared in GATE Mechanical 2013 paper, IIT Mumbai paper. The question says a hinged gate of length 5 meter inclined at 30 degree with the horizontal and with a water mass on its left is shown in the figure below. Density of water is 1000 kg per meter cube. The minimum mass of gate in kg per unit width perpendicular to the paper required to keep it closed is equal to how much? Options are also given. Answer is in kg and the width of this gate perpendicular to the screen is equal to 1 unit. Now the gate is not particularly visible. Let me highlight it. Let us say there is a hinge over here. From this hinge you are having a gate. This, let us say, is a gate over here. Let me call this gate as some OA gate, for example. The length of this gate is equal to 5 meter and the gate happens to be inclined at an angle of 30 degree with respect to horizontal. This is a hinge over here. Now, the word that is important to solve this question is minimum mass. The minimum mass of the gate required in kg is equal to how much? Now, if you are looking at minimum mass condition, that means the gate is just about to open. Please understand some points over here. Minimum mass condition. What does it imply? It implies gate is about to open. About to open. If the gate is about to open, that means the contact at point A is being lost. The contact at point A is just lost. Is just lost. अब देखिए, if the contact is being lost, therefore the normal action reaction pair at point A must become equal to 0. This is very important point. Therefore, the normal action reaction at point A must become equal to how much? 0. And since the gate is about to open, I can use multiple words for about to open. I can also say gate is impending to open. Gate is at the verge of opening. All these things are indicating that equilibrium is valid. Equilibrium is valid. You will be observing many questions from the concept of hydrostatic forces will eventually convert into equilibrium questions. Okay? Now, how do we solve this particular question? To solve this question, let us say we are drawing the free body diagram of this gate. If you draw the free body diagram of gate, let us say the gate is something like this. This is a point O we have chosen, certain point O we have chosen. This is another point we have chosen. This point happens to be some point A. Point O is having hinge. Since it is having hinge, therefore it is supposed to have two hinge reactions. Let us say at point O, we are having a horizontal hinge reaction at point O and we have a vertical hinge reaction at point O. There are two reactions. Point A is in contact with the surface, it is just losing contact. So we know that the normal force at point A is equal to how much? It is equal to 0. Normal force at point A is equal to 0. Now, let us say this gate over here is having a center. This point is point G, center of plate. We know for sure since it is an inclined surface, therefore the center of pressure is supposed to lie below G. So center of pressure is lying somewhere over here. This is a point at which you are having the center of pressure lying. At this particular point, you are having the hydrostatic force acting. And remember, hydrostatic force is by the virtue of intensities of pressure. Since all the intensities of pressure are normal, that is perpendicular, therefore hydrostatic force also will be perpendicular. So this is your hydrostatic force F. And F is equal to how much? Gamma area H bar. You have seen the formula some time back. F is equal to gamma area H bar. It is acting purely perpendicular. It is acting purely perpendicular to the plate. Purely perpendicular to the plate. This is the value of F we are having. Now you see, this F is creating a moment which is trying to open this gate up. The gate is something like this, hinged at this point. Now by the virtue of F acting over here, the gate is about to open up. There has to be a resisting moment if you want to stop this particular opening up. If you want to avoid the opening of this gate, there has to be a resisting moment. You are not applying any torque. But what you are allowing is, you are allowing the weight to create some moment over here. There is weight present and that weight is responsible for creating a counter moment. Now you see the weight present over here is supposed to pass through point G. This is weight, let us say. And the formula for weight happens to be equal to how much? Weight is equal to mg. This is creating a counter moment. Now, if it is about to open, equilibrium is valid, therefore I can start my solution by saying summation of moment about point O is equal to 0. Now you might be wondering why I have chosen this particular equation. The reason being, right now I am having 4 forces present. You remove off normal force, so we are having 4 forces present, of which I wish to find out the value of mg. I don't want to deal with these 2 forces, vertical and horizontal at point O are something which are unnecessary for me. I don't want to deal with them. How do I avoid dealing with them? I realize both these forces are passing through point O. Try to eliminate these 2 forces by choosing a moment about this point. They will not be creating any moment about that point. So therefore I have gone for the equation summation of moment about point O is equal to 0. Now if I say summation of moment about point O is equal to 0, summation of moment about point O is equal to 0, what do I get from there? I get from there the moment by the virtue of force, let us say anti-clockwise moment and the clockwise moment must be equal in magnitude. So I can say force F multiplied to lever arm must be equal to mg multiplied to its lever arm. Now how much are these lever arms we have to see. Force F multiplied to a lever arm and mg multiplied to a lever arm. First of all, mg multiplied to how much lever arm will we be having? Now you see, from point O to point G, the length is basically half the length of this plate. The entire length of this plate was 5 meter, therefore this distance happens to be equal to half of 5, that is 2.5 meter. This is the length we are having. From where to where? Point O to point G. The lever arm over here is supposed to be the perpendicular distance. The lever arm is supposed to be the perpendicular distance from point O till this force. If you look at the perpendicular distance, I hope you are able to see this thing. This perpendicular distance जो है ना, that is your lever arm. That is your lever arm. How much is that perpendicular distance equal to? You know that this plate is inclined at an angle theta equal to 30 degrees. Theta equal to 30 degrees. Now you know these 2 lines over here, the blue line I have drawn and this line, both are parallel and the gate is acting as a transversal over here. So this angle theta and this angle both are supposed to be same, that is also equal to 30 degrees. So therefore the lever arm over here is supposed to be equal to how much? 2.5 cos 30. I hope you are following this thing. This is supposed to be 2.5 cos 30. So I can write 2.5 cos 30 over here. 2.5 cos 30. ठीक है. Next thing, I need to know the value of lever arm of F. For finding, this is where I am taking the advantage of pressure prism. I am making use of pressure prism over here. One moment please. One moment please. ठीक है. Now if you see, if you look at this particular image, we realize that over here the pressure is equal to 0 and as you keep on going down the pressure is linearly increasing. As you keep going down, if you draw the pressure distribution diagram, the pressure is linearly increasing. So let us say this is a plate you are having. This is O, this is certain point A. And as you keep moving down, the pressure is keeping on increasing linearly. Okay. If you imagine the pressure prism diagram, the prism diagram is supposed to be 1 unit width. You compound this with 1 unit width, you will get a pressure prism diagram. Okay. Now I can say logically, since it's the triangular kind of loading, my net load should be concentrated my net force is supposed to be concentrated. If this entire length is L, it should be concentrated at a distance of L by 3. You should be knowing in a triangle, the centroid is given by this particular way, L by 3. That means this distance is supposed to be equal to how much? It is supposed to be equal to 2L by 3. It is supposed to be equal to 2L by 3. Using this logic, I can orally say the lever arm over here, this distance over here is equal to how much? It is equal to 2L by 3. L is equal to how much? L is equal to 5. So 2 into 5 by 3 is equal to 10 by 3 meter. This is equal to 10 by 3 meter. So this value is 10 by 3. This is what I'm having. Okay. Moving further. The value of force is equal to how much? Force is equal to gamma, that is rho g, into area. Area is equal to how much? 5 times 1, that is the area. The plate's area is 5 unit length multiplied to 1 unit length over here, multiplied to h bar. Ab dekhiye h bar is equal to how much? Very simple. H bar is the vertical distance over here. This vertical distance is h bar. And the value of h bar should be equal to how much? Think logically. H bar would be equal to 2.5, this time sine 30 would come. 2.5 sine 30. 2.5 sine 30. So the value of h bar is equal to 2.5 sine 30. This is the value of force we are having. Gamma, area, h bar. Multiplied to lever arm. Lever arm is equal to how much? 10 by 3. This has to be equal to how much? This has to be equal to mg into 2.5 cos 30. 2.5 cos 30. Now you see I can cancel off on either side. I am having g and 2.5. I can cancel them off. G and 2.5 got cancelled off. My aim is to find out this mass m over here. So what do I get from here? I get from here the mass m is equal to how much? Mass m is equal to 5 into rho, that is 5,000, because rho is equal to 1,000, no? Multiplied to 10, so 50,000, multiplied to sine 30, divided by, you see over here, you are having cos 30 over here. 3 also is here, 3 is present, multiplied to cos 30. That is equal to how much? That is equal to 50,000 divided by 3 tan 30. Rather tan 30 would come over here. Tan 30 would come over here. What is tan 30 equal to? 1 by root 3. This is equal to 50,000 divided by 3 root 3. These many kg is the answer. 50,000 divided by 3 root 3. See, if you look at the options, you may as well avoid the calculator. Look at the options over here. 5,000, 6,600, 7,546, 9,623. You can make a decent guess. You see, 3 root 3. It's important, especially if you are preparing for IES, to avoid calculator as much as possible. See, you don't have to exactly get the answer. You have to get the correct option. No one is demanding from you the correct number. They are demanding from you the correct option in IES. Okay, there's a difference between these two things. Now what I can do is, I realize root 3 happens to be equal to how much? 1.732. 1.732. Let us say, for the sake of understanding, it is 1.7, for example. 3 times 1.7 would be 5.1. If it is 5.1, this value has to be slightly less than, see, 50,000 here divided by 5.1, slightly less than, the value is slightly less than 10,000. It is supposed to be slightly less than 10,000. Because you are having 50,000 divided by 5.1 or 5.2, let us say, for example. 5.1 or 5.2, so slightly less than 10,000. Which option you are seeing is slightly less than 10,000? The only option you are seeing which is slightly less than 10,000 is 9,623. So correct answer over here is 9623 kg. I hope this is clear to all of you. Let us take one more numerical. We have some time now. Let us take one more numerical. Look at this. The question over here is saying the gate shown will open automatically when the water level reaches a certain height above the hinge. Determine the height h if the value of b is equal to 1.6 meter. You have to find water level. There is water supposed to be present over here. Excuse me. This is water, let us say, and this is the height h we are having. Okay. Now you are realizing in this particular diagram, 1 minute. In this diagram, let us say, this is the water level, this is the height h we are having, and this is b over here. You are realizing the force acting over here, is creating a clockwise moment, and the force acting, hydrostatic force acting over here, is creating an anti-clockwise moment. Now the gate will be just opening up at the moment the clockwise moment and anti-clockwise moment, both of them become equal. When clockwise and anti-clockwise moment both become equal, that is when the gate is about to open up. So if you draw the free body diagram of this particular setup, the free body diagram would be something like this. Imagine over here, 1 second, this is a water level we are having. Again, if I draw the pressure prism diagram over here, I'll be having a triangular kind of loading. This is a triangular kind of loading. Okay. The value of pressure over here has to be equal to gamma h. And on this portion, if I draw pressure prism diagram, over here also the pressure is equal to gamma h. Let us say, 1 second please. Over here also the pressure is equal to gamma h and gamma h. You see, this portion of the gate is a horizontal portion, therefore the pressure intensity remains constant, something like UDL, uniformly distributed load. Okay. Now this pressure intensity is up to a height h, and this is b over here, this is b. Okay. By the virtue of these pressure intensities, you are going to have a certain force. This force is F1, let us say, F1. And we know very well that with respect to this particular point, the force is supposed to act at a distance of how much? At a distance of h by 3. Again, the reason being you are having a triangular kind of loading. And over here, let us say you are having a force acting exactly at the center at a distance of b by 2. You are having a force acting. This distance over here is b by 2. This force over here is F2 force. The force over here is F2 force. Achha, F1 would be equal to how much? Imagine the width over here is 1 unit. Okay, imagine the width is 1 unit. F1 would be equal to how much? It is volume of pressure prism. Volume of pressure prism is equal to cross section of this diagram multiplied to the width. Width 1 unit hai. So the cross section of this particular diagram is equal to half base gamma h, height h. So gamma h into h is gamma h square. This is F1 value. Multiply to 1 unit width, so therefore don't need to worry about the width over here. F2, again, it is equal to how much? It is equal to area of this particular diagram multiplied to width. So gamma h multiplied to b multiplied to 1 unit. So this is gamma hb. This is what we are having. At point O, you will be having, let us say this point is some point O over here. You will be having some hinge reactions, but if I take moment about point O, I don't have to worry about hinge reactions. Apart from that, the stop provided over here is supposed to give you a reaction. It is supposed to give you a reaction. Stop over here would give you a reaction, let us say. reaction from the stop. There was a stop present over here. But when it is about to open up, the gate is about to open up, the reaction from the stop will become equal to 0. Okay, this is what we are having. Now again I can write similar kind of equation what I had some time back. One moment please. I can write an equation saying summation of moment about point O is supposed to be equal to 0. Therefore, the clockwise moment is supposed to be anti-clockwise moment, which implies half gamma b h square multiplied to h by 3 must be equal to, one second, I have made a mistake over here, let me correct it. Half gamma h square multiplied to h by 3 is equal to, half gamma h square multiplied to h by 3 is equal to gamma hb multiplied to b by 2. So b square by 2. You can cancel off 1h and 1h on either side. You can cancel this off. But mind you, when you are cancelling this off, you are basically disregarding a solution. And that solution is h is equal to 0. Anyway, that solution is not important to us, but you should know these things. Whenever you are cancelling off a particular unknown, that time that unknown's value is equal to 0 also is a valid solution. Anyway, gamma also can be cancelled off over here. The value of h would become equal to how much? 2 also got cancelled off. H would become over here equal to b root 3. H would be equal to b root 3. The value of b given to you in the question was 1.6. Root 3 is equal to 1.732. Again, I want you to make a decent guess over here. Okay, 1.6 into 1.6 is 2.56. It is 2.56. And this has greater than 2.56. Now look at the options, greater than 2.56. You are having 2.77 and 2.91. Guarantee these two options are wrong. If it is in gate, you can use calculator very easily, no problem. I'm talking about if IES examination, then what do you do? Next thing, 2.91. 1.6 multiplied to how much would give you 2.91? It should exceed 1.8. 1.6 multiplied to 1.8 would give you, let us say, 2.88, let us say. It would give 2.88, nearly something like that. Now, therefore, the answer is supposed to be, in this particular case, 2.77 meter, let us say. The answer is 2.77 meter. The answer over here has to be 2.77 meter. I hope these questions are clear to you, and this practice is good enough to understand the concept of hydrostatic forces. And if you still have any difficulties, you can refer to this video again. It will be available on the channel. Thank you and all the best to all of you.